Good morning everyone, welcome to this session. Today we are going to explore a very important and practical topic in nuclear engineering. Dispersion type fuel and silicide fuel systems which are widely used in research reactors. अगर आप न्यूक्लियर इंजीनियरिंग रिएक्टर टेक्नोलॉजी या एडवांस फ्यूल सिस्टम में इंटरेस्ट रखते हो तो ये सेशन आपके लिए काफ़ी यूजफुल होने वाला है. Before we begin, a quick note, I regularly upload content on this channel every Monday, Wednesday and Friday covering topics related to nuclear engineering, artificial intelligence and electrical control systems. So if you want to stay updated with the real technical knowledge and practical insights, make sure you subscribe to the channel and stay connected. Now coming back to today's topic in this lecture, we will not just see what dispersion fuel is, but we will understand why it is used, how it is designed, how it is actually fabricated in the real systems. We will not take any real time technical data. हम बेसिक से स्टार्ट करेंगे and then gradually move towards more advanced concepts like silicide fuel and its applications. So before we go into dispersion fuel directly, let us first build a strong foundations by understanding what exactly is nuclear fuel and how it functions inside a reactor. Now let us clearly understand the objective of this lecture. The goal here is not just to define dispersion fuel but to build a complete conceptual and practical understanding of the system. First we will start with the fundamental of nuclear fuel, what it does inside the reactor and what parameters define its performance. उसके बाद हम dispersion fuel का core concept देखेंगे, यानी कि कैसे फ्यूल प्रैक्टिकल्स एक मैट्रिक्स के अंदर डिस्ट्रीब्यूट होते हैं और उसका एडवांटेज क्या होता है. देन वी विल फोकस स्पेसिफिकली ऑन सिलिसाइड फ्यूल, दैट इज U₃Si₂AL, which is the modern and widely adopted fuel in research reactor. Along with that we will go step by step through fabrication concept, because real understanding तब आता है जब हम डिज़ाइन के साथ साथ मैन्युफैक्चरिंग को भी समझते हैं. फाइनली वी विल कनेक्ट एवरीथिंग टू एक्चुअल रिएक्टर एप्लीकेशंस इंक्लूडिंग बोथ ग्लोबल प्रैक्टिसेस एंड इंडियन कॉन्टेक्स्ट. सो द आइडिया इज बाय द एंड ऑफ दिस लेक्चर you should be able to understand not only the theory but also engineering behind dispersion fuel system. अब जब ऑब्जेक्टिव क्लियर हो गया, लेट अस मूव टू द मोस्ट फंडामेंटल क्वेश्चन, व्हाट एग्जैक्टली इज द न्यूक्लियर फ्यूल एंड व्हाट रोल डज इट प्ले इनसाइड ए रिएक्टर सिस्टम. So let us understand the fundamental concept about nuclear fuel. It is the material inside the reactor core that undergoes fission and produces energy in the form of heat. Along with heat, it also releases neutrons which are essential to sustain the chain reaction. लेकिन सिर्फ हीट जनरेट करना ही काफ़ी नहीं है, फ्यूल को irradiation conditions के अंदर स्ट्रक्चरली स्टेबल भी रहना है, which is very critical requirement. So in simple terms, nuclear fuel has to perform three roles simultaneously. First, it must generate heat. Second, it must support neutron economy. Third, it must maintain its structural integrity under extreme condition. That is why fuel performance depends on three major aspects: thermal behavior, neutronic efficiency and mechanical stability. अगर इन तीनों में imbalance होता है तो fuel failure का risk बढ़ जाता है. Now what we understand what nuclear fuel does, the next logical step is to see how different types of fuels are classified and where dispersion fuel fits in this classification. So let us now see how nuclear fuels are broadly classified. These are three main categories: ceramic fuel, metallic fuel and dispersion fuel. Ceramic fuels like uranium oxide or MOX are mainly used in power reactors. They are stable at high temperature, can achieve high burn up. Metallic fuel on the other hand have high thermal conductivity, लेकिन उनमें फेज ट्रांसफॉर्मेशन एंड डायमेंशनल स्टेबिलिटी इश्यूज हो सकते हैं, स्पेशली एट हाई टेम्परेचर, एंड इट इज़ अंडर एडवांस स्टेज एंड फर्दर रिसर्च स्टेज. Now coming to the most important category for today, dispersion fuel. In dispersion fuel, fuel is not just present as continuous solid, instead it is present as small particles distributed inside a matrix material. ये कॉन्सेप्ट स्पेशली रिसर्च रिएक्टर के लिए डेवलप किया गया है जहाँ हीट रिमूवल और स्टेबिलिटी बहुत क्रिटिकल होता है. सो अनलाइक सिरेमिक और मेटलिक फ्यूल, डिस्पर्सन फ्यूल इज एक्चुअली ए कंपोजिट सिस्टम, नॉट ए सिंगल मटेरियल. नाउ द क्वेश्चन इज, अगर ऑलरेडी सिरेमिक और मेटलिक फ्यूल्स अवेलेबल है तो डिस्पर्सन फ्यूल की ज़रूरत क्यों पड़ती है. So in this next slide, let us understand why research reactors specifically require dispersion type fuels. Now let us understand the real engineering reason behind dispersion fuel. Research reactors operate under very different conditions compared to power reactor. They are designed to produce high neutron flux, often for isotope production, irradiation experiment. इसका मतलब है कि कोर कॉम्पैक्ट होता है और लोकल पावर डेंसिटी काफ़ी हाई होती है. As a result, the surface heat flux can reach value in the range of 200 to 300 watts per square centimeter. Now, under such conditions, heat removal becomes a critical challenge. If we use conventional ceramic fuels, their thermal conductivity is low, which can lead to local temperature rise and hotspot formation. Metallic fuels have better conductivity, लेकिन उनमें phase instability और swelling issues आ जाता है under irradiation. So the problem is clear. We need a fuel system that can efficiently remove heat, maintain dimensional stability and sustain high neutron flux condition. That is where dispersion fuel comes in. In the dispersion fuel, the fissile material is broken into fine particles, and these particles are embedded in a high thermal conductivity matrix like aluminium. इससे हीट ट्रांसफर पाथ इम्प्रूव होता है और लोकल टेम्परेचर ग्रेडियंट रिड्यूस हो जाता है. नाउ व्हाट वी अंडरस्टैंड व्हाई डिस्पर्शन फ्यूल इज नीडेड, लेट अस मूव टू नेक्स्ट स्टेप. What exactly is the structure of a dispersion fuel plate and how this concept is implemented physically? Dispersion fuel is essentially a composite fuel system consisting of two distinct phases: the dispersoid, which is the fissile material, and the matrix, which is continuously supporting the phase. The dispersoid can be materials like UAlx, U₃Si₂, uranium oxide, U₃O₈, while the matrix is typically aluminum in most research reactor application. अब सबसे इम्पॉर्टेंट कॉन्सेप्ट यह है कि फ्यूल यहाँ एक कंटिन्यूस सॉलिड ब्लॉक के फॉर्म में नहीं होता है. इंस्टेड इट इज प्रेजेंट एज डिस्क्रीट particles uniformly distributed inside the matrix. This changes the entire heat transfer behavior. Since the matrix is continuous and has high thermal conductivity, heat generated inside the fuel particles can quickly transfer through matrix to the coolant. इससे टेम्परेचर ग्रेडियंट से रिड्यूस होता है और लोकल हॉटस्पॉट फॉर्मेशन का रिस्क सिग्निफिकेंटली कम हो जाता है. Additionally, the matrix also provides a mechanical support and acts as a secondary barrier, limiting direct interaction between fuel and coolant system. So dispersion fuel is not just a material, it is carefully engineered composite system. Now what we understand the basic concept, the next step is to see how this is physically realized in the form of fuel plate structure. Now let us see how the dispersion fuel concept is actually implemented in physical form. In most research reactor, dispersion fuel is used in a plate type geometry, often referred to as MTR type fuel. The central part of this plate is called the fuel meat, which consists of mixture of fuel particles and aluminum matrix. This region is carefully controlled in thickness to ensure proper heat removal. In fuel meat एक स्ट्रक्चर होता है जिसे हम पिक्चर फ्रेम बोलते हैं. दिस फ्रेम डिफाइंस द बाउंड्री ऑफ द फ्यूल रीजन, ensure dimensional stability during fabrications and operations. On both sides of this assembly we have cover plates or cladding, typically aluminum alloy, which acts as the primary barrier between fuel and coolant. So overall the structure becomes a sandwich: cover plate, fuel meat within frame and another cover plate. Multiple such plates are arranged in parallel with coolant channels between them, allowing efficient heat removal. इस डिज़ाइन का मेजर एडवांटेज है कि हाई surface area to volume ratio, which directly improves heat transfer efficiency. Now that we understand the physical structure, the next important question is, what are the key design parameters that control the performance of this dispersion fuel system? Now let us discuss the most important design parameter that control the behavior of dispersion fuel. The first parameter is the fuel volume fraction, usually denoted as VF. This represents how much of the fuel meat is occupied by fissile particle. Typically it is limited to around 40 to 50% because beyond this matrix phase starts losing its continuity. और अगर मैट्रिक्स कंटिन्यूअस नहीं रहेगा तो हीट ट्रांसफर सिग्निफिकेंटली डिग्रेड हो जाएगा. द सेकेंड पैरामीटर इज द पार्टिकल साइज ऑफ द डिस्पर्सोइड. पार्टिकल साइज डायरेक्टली अफेक्ट्स हाउ फिशन फ्रैगमेंट्स इंटरेक्ट विद द सराउंडिंग मैट्रिक्स. स्मॉलर पार्टिकल्स में लीड टू हायर सरफेस एरिया एंड मोर इंटरेक्शंस व्हिच while larger particles can localize the damage differently. The third important parameter is particle spacing and distributions. Fuel particles should be uniformly distributed without clustering. If clustering होता है तो local heat generation increase हो सकता है और heat removal uneven हो जाता है. So overall the design objective is to maintain continuous matrix network, ensure proper spacing and balance fuel loading with thermal performance. In short, dispersion fuel design is a balance between reactivity, heat transfer and structural stability. Now based on this parameter, a very important physical phenomena arises during irradiation which is called fission fragment recoil zone. That is what we will discuss next. Now we come to the most critical concept in the dispersion fuel design, the fission fragment recoil zone, FFRZ. During nuclear fission, a large portion of the energy, around 80%, is carried away by the fission fragments themselves. These fragments have very high kinetic energy, typically in the order of tens of MeV per fragment. अब तक ये हाई एनर्जी फ्रैगमेंट्स फ्यूल पार्टिकल के अंदर जनरेट होता है. दे ट्रैवल अ स्मॉल डिस्टेंस, टिपिकली इन माइक्रोन रेंज, interact with both the fuel particle and the surrounding matrix. This creates a localized damage region around each fuel particle which we call the fission fragment recoil zone. Now the most important design condition is that these recoil zones should not overlap. अगर adjacent particles के FFRZ overlap करते हैं तो matrix damage accumulate होने लगता है. This leads to increased swelling, reduction in thermal conductivity and eventually can result in fuel degradation or failure. So this concept directly controls how we select particle size, spacing and fuel loading. In simple terms, FFRZ defines the safe operating limits of dispersion fuels under irradiation. Now that we understood this critical phenomena, let us move ahead and see what types of dispersion fuel systems are used in practice, especially in aluminum matrix system. Now let us look how a dispersion fuel system have evolved over time, especially in aluminum matrix fuel. Initially the most commonly used system was UAlx AL, where uranium aluminum intermetallic compounds were dispersed in aluminum matrix. This system had good compatibility with aluminum, लेकिन इसका uranium density relatively low था, which limited the achievable burn up and reactor performance. To overcome this, the next stage of development was U₃O₈ AL dispersion fuel. Here uranium oxide was used, which allowed higher uranium loading compared to UAlx and improves overall fuel performance. लेकिन फिर एक मेजर रिक्वायरमेंट आया, ग्लोबल शिफ्ट फ्रॉम हाई enriched uranium to low enriched uranium, that is below 20% U₃35. So इस ट्रांजिशन को सपोर्ट करने के लिए हायर यूरेनियम डेंसिटी फ्यूल की जरूरत थी. दिस लेड टू डेवलपमेंट ऑफ U₃Si₂ AL dispersion fuel, which offers significantly higher uranium density, typically around 4.8 to 6 gram per uranium per cubic centimeter. Along with that, it also shows better irradiation behavior and supports LU based reactor operations. So today U₃Si₂ AL has become a modern standard for research reactor fuel system. Now what we understand the evolution, let us go deeper into why U₃Si₂ is specifically preferred and what makes it superior as a fuel material. Now let us understand why U₃Si₂ has become the preferred fuel material in modern dispersion fuel system. The most important advantage of U₃Si₂ is its high uranium density, typically in the range of about 4.8 to 6 grams of uranium per cubic centimeter. इसका डायरेक्ट इम्पैक्ट ये है कि हम लो एनरिच्ड यूरेनियम यूज करते हैं और रिक्वायर्ड रिएक्टिविटी अचीव कर पाते हैं, which is critical for global non-proliferation requirement. Secondly, because of higher uranium loading, U₃Si₂ supports higher burn up within a limited fuel volume, which is a very useful concept for compact research reactor cores. From a thermal point of view, U₃Si₂ also performs better compared to oxide fuels. It has the relatively better thermal conductivity, which helps in reducing internal temperature gradients. अब irradiation behavior की बात करें तो U₃Si₂ shows more controlled swelling characteristics and maintains better structural integrity compared to earlier system. If we compare UAlx had lower density, U₃O₈ has higher density but poorer thermal behavior. But U₃Si₂ gives a balanced combination of density, thermal performance and irradiation stability. That is why it has become the standard choice for modern research reactor fuel. Now what we understand its advantage, the next point is how does U₃Si₂ actually behave under irradiation inside the reactor environment. Now let us understand how U₃Si₂Al dispersion fuel behaves under actual reactor irradiation conditions, which when fission occurs inside the fuel particles, it produces fission gas like xenon and krypton. These gases accumulate within the particles and form bubbles which grow with increasing burn up. अब ये bubble formation directly swelling behavior को affect करता है. अब fission products accumulate हो रहा है, the fuel undergoes volumetric expansion which we call swelling. Swelling का extent depend करता है high burn up और operating temperature पर. Another important phenomenon is fuel matrix interaction. At elevated temperature, U₃Si₂ particles react with the surrounding aluminum matrix, forming intermetallic phases, often referred to the interaction layer. This layer can affect heat transfer properties because it has lower thermal conductivity compared to pure aluminum. Along with this irradiation, it introduces defects in this material which further reduces the overall thermal conductivity of the fuel meat. So over time, as burn up increases, heat transfer becomes less efficient, temperature gradients may increase. That is why parameters like particle size, distribution matrix continuity and operating temperature becomes critical for long term fuel performance. Now what we understand that the behavior under irradiation, let us move to the most practical important part, how this fuel is actually fabricated step by step. Now we have come to the most practical and important part of this lecture, the fabrication of U₃Si₂Al dispersion fuel. The fabrication follows a powder metallurgy route, where we start from elemental powder and finally produces fully bonded fuel plate. First, uranium and silicon powders are prepared and blended, followed by compaction to form green compacts. Then these compacts are subjected to high temperature synthesis in a vacuum furnace where the U₃Si₂ compound is formed. इसके बाद synthesized materials को क्रश और सीव किया जाता है to obtain the required particle size distribution. These particles are then mixed with aluminum powder to form the fuel meat matrix. The mixture is placed inside a picture frame, assembled with cover plate, welded to form a sandwich structure. After that, bonding is achieved through hot rolling and cold rolling process, followed by a blister test to ensure bond integrity. Finally, cleaning, radiography, dimensional inspections are carried out before assembling the plate into fuel system. So overall fabrication is a multi-step, tightly controlled process where each stage directly affects. Now let us go through the initial stages of fabrication, starting from powder preparation to silicide formation. The process begins with uranium metal powder and silicon powder taken in a carefully controlled stoichiometric proportion to form the desired silicide compound. These powders are then dry blended to ensure uniform distribution. ये step बहुत important है क्योंकि uniformity directly affect करता है कि final compound formation और उसकी quality. After blending, the powder mixture is compacted using a high hydraulic press to form green compacts. इस स्टेज पर ऑब्जेक्टिव होता है हाई डेंसिफिकेशन अचीव करना ताकि फार्नेस प्रोसेसिंग यूनिफॉर्म हो. Next comes the thermal synthesis stage. The compacts are heated in a controlled vacuum environment where a multi-stage heating cycle is followed. The heating is done gradually to avoid thermal stress and cracking. यहाँ पर यूरेनियम और सिलिकॉन रिएक्ट करके एक स्टेबल इंटरमेटालिक कंपाउंड बनाते हैं जो कि U₃Si₂ फेज होता है. एट द सेम टाइम ऑक्सीडेशन और कंटामिनेशंस को अवॉइड करना बहुत क्रिटिकल होता है, इसलिए वैक्यूम कंडीशंस मेंटेन किया जाता है. सो दिस स्टेज इज एसेंशियली अबाउट कन्वर्टिंग रॉ पाउडर्स इनटू ए केमिकली एंड स्ट्रक्चरली स्टेबल कंपाउंड्स. Now that compound is formed. Next step is to convert into usable particles formed through crushing, sieving and mixing with aluminum matrix. Now let us move to the next stage of fabrication where synthesized silicide compound is converted into a usable fuel form. First the compound is mechanically crushed, then passed through a sieve to obtain control particle size distribution. यहाँ पर पार्टिकल साइज कंट्रोल बहुत क्रिटिकल होता है क्योंकि ये डायरेक्टली स्वेलिंग बिहेवियर और हीट ट्रांसफर को अफेक्ट करता है. ओवरसाइज पार्टिकल्स और वेरी फाइन पार्टिकल्स दोनों को रिमूव किया जाता है टू मेंटेन कंसिस्टेंसी. नेक्स्ट दीज पार्टिकल्स आर मिक्स्ड विथ एल्यूमिनियम पाउडर फॉर्मिंग व्हाट वी कॉल द फ्यूल मीट मिक्सचर. इस स्टेज पर यूनिफॉर्म डिस्पर्सन इंश्योर करना बहुत इंपॉर्टेंट है ताकि फ्यूल पार्टिकल्स इवनली डिस्ट्रीब्यूट हो जाए मैट्रिक्स के अंदर. आफ्टर दैट द फ्यूल मीट इज प्लेस्ड इनसाइड एन एल्यूमिनियम पिक्चर फ्रेम एंड कवर प्लेट्स आर पोजिशन्ड ऑन बोथ साइड्स. दिस असेंबली इज देन एज वेल्डेड forming a sealed sandwich structure. Now comes the bonding stage. First hot rolling which creates metallurgical bonding between layers, followed by cold rolling to achieve final thickness and dimensional accuracy. Finally the plate undergoes blister testing to check bond integrity, followed by cleaning radiography inspection to verify fuel meet position. So this completes the transformation from powder to a fully formed fuel plate. Now what we understand fabrication, let us see how this fuel behaves during operation in terms of heat transfer and performance characteristics inside the reactor. Now let us understand how dispersion fuel behaves from a thermal point of view inside the reactor. During operation, fission occurs inside the fuel particles and heat is generated at those locations. This heat must travel through multiple layers, first from the fuel particles to the aluminum matrix, then to the cladding and finally to coolant flowing between the plates. यहाँ पर aluminum matrix का रोल बहुत क्रिटिकल हो जाता है because aluminum has high thermal conductivity. It provides continuous and efficient path for heat transfer. इससे local temperature gradients reduce हो जाता है और heat uniformly distribute होता है across the plate. The research reactors, the surface heat flux is quite high, so maintaining a uniform temperature distribution becomes essential. अगर heat removal efficient नहीं लगा तो local hotspots develop हो सकते हैं which can lead to fuel degradation. Dispersion fuel design ensure that heat is quickly conducted away from the fuel particles, improving overall safety margins. So from a thermal perspective, the matrix is not just a support, it is the primary heat transfer medium in the system. Now that we understand heat transfer, let us move further and see what happens over time, how fuel degrades and what are the failure mechanisms under irradiation. Now let us understand how dispersion fuel degrades over time and what are the possible failure mechanisms. One of the primary mechanism is swelling of fuel particles. As fission continues, fission products accumulate inside the particles leading to volume expansion which increased with burn up. इसके साथ साथ fission gases like xenon and krypton also gets generated, forming gas bubbles inside the particles. These bubbles grow over time and create internal stress within the fuel matrix. Another important mechanism is the interaction between U₃Si₂ and the aluminum matrix. At operating conditions, an interaction layer form around the fuel particles which can affect both thermal and mechanical properties. ये interaction layer generally aluminum के साथ thermal conductivity रखता है, इसलिए overall heat transfer efficiently reduce हो जाता है. As a result, temperature gradient increases and the risk of local hotspots become higher. At extreme cases, these combined effects can lead to blister formations, debonding of layers and local deformation of the plate. So, understanding these gradients and degradation mechanism is essential for predicting fuel life and ensuring safe operation. Now, what we have seen, fuel behaves and degradation mechanism. Now, let us move towards the practical side, how these fuels are used in real reactors both globally and in India. Now let us see how dispersion fuel systems are actually applied in real reactor. Globally there has been a major transform from high enriched uranium to low enriched uranium, mainly driven by non-proliferation requirement. इस ट्रांजिशन को सपोर्ट करने के लिए RERTR प्रोग्राम इनिशिएट किया गया है, जिसका ऑब्जेक्टिव रिसर्च रिएक्टर को LU बेस्ड फ्यूल पर कन्वर्ट करना. एज ए रिजल्ट U₃Si₂ UAl dispersion fuel emerged as the standard solution because it provides higher uranium density while still operating below 20% enrichment. These fuels are widely used in material test reactors and research reactors across the world. अगर हम इंडियन कॉन्टेक्स्ट में देखेंगे तो इनिशियली APSARA reactor used UAlx Al fuel with highly enriched uranium. Later, with the upgraded versions of APSARA-U, the fuel was converted to U₃Si₂ Al dispersion fuel using LEU, aligning with global practices. These fuels are used for a variety of applications including radioisotope productions, neutron activation analysis, material irradiation studies. So, dispersion fuels plays a very important role not just in reactor operation but also in scientific research and healthcare application. Now what we have seen applications, let us move to final stage, quality control and safety aspects which ensures reliable fuel performance. Now let us discuss the final and very important aspects, quality control and safety in dispersion fuel fabrication. Since dispersion fuel is a multi-stage process, the quality control is required at every step. Starting from powder stage, we ensure proper compositions, homogeneity and particle size distributions because these directly affect irradiation performance. Fabrications के दौरान भी strict control maintain किया जाता है, especially during mixing, compaction and rolling process, ताकि uniform bonding और dimensional accuracy achieve हो सकते हैं. One of the most critical test is blister test, which checks the integrity of bonding between the layers. अगर bonding weak है तो हीटिंग एलिन के दौरान ब्लिस्टर फॉर्म होगा और प्लेट रिजेक्ट कर दिया जाता है. अनदर important inspection is radiography or X-ray, which helps confirm the position and uniformity of the fuel meat inside the plate. Along with that, dimensional checks and ensure that thickness and tolerances are within acceptable limits. From a safety point of view, dispersion fuel follow a multi-layer barrier concept. Fuel particles, matrix and cladding together ensures containment and heat removal. So overall, the strict quality control ensures reliable performance and safe reactor operation. Now with this we come to the final slide. We will summarize and see what are the key takeaways. So let us conclude this here. Dispersion fuel is essentially a composite fuel system, as we have understood, where fuel particles are dispersed within a matrix designed specifically to handle high heat flux and compact reactor conditions. We saw that among different material system, U₃Si₂ Al silicide has become the preferred choice due to its high uranium density, compatibility with highly enriched low enriched uranium and improved irradiation performance. Fabrication plays a critical role. Multi-stage control है, complex तो है ही, where parameters like particle size, volume fractions, bonding quality directly influence the final fuel behavior. Performance wise, everything comes down to a balanced heat transfer efficiency, irradiation stability and structural integrity. अगर इन तीनों पैरामीटर्स प्रॉपरली बैलेंस हो जाए तो फ्यूल सिस्टम सेफ और एफिशिएंट दोनों होता है. सो ओवरऑल डिस्पर्सन फ्यूल इज नॉट जस्ट ए मटेरियल बट ए केयरफुली इंजीनियर सिस्टम integrating material science, reactor physics and fabrication technology. Thanks for your attention. अगर आपको ये लेक्चर यूजफुल लगा तो मेक श्योर टू सब्सक्राइब टू द चैनल, जहाँ पर मैं रेगुलरली कंटेंट शेयर करता हूँ और न्यूक्लियर इंजीनियरिंग एआई एंड इलेक्ट्रिकल सिस्टम्स के ऊपर. वी विल कंटिन्यू एक्सप्लोरिंग मोर सच एडवांस टॉपिक्स इन अपकमिंग सेशंस. थैंक यू.